Okay, so today we're going to look at the homework solutions to the acid-base chemistry homework, which is chapter 20 in your book. The first question asks you to classify a list of species as either strongly acidic, strongly basic, weakly acidic, or none of the above. So you get your strong acids from table 21 as well as your strong bases. Now, if you look at table 20.1, you will see that you'll see the strong acids listed. There's only there's only 6 of them. So you look on that list and you compare it to the list I gave you, and you just check them off. There's no way to figure out what a strong acid is or a strong base based on looking at the structure. You just have to have them memorized. So the strong acids are going to be H2SO4, it's going to be HCl, HI, and HClO4. Those are going to be your strong acids. Now your weak acids are going to be anything that's an acid that is not on the list of strong acids. So that would be CH3COOH. It would also be C6H5COOH. The first one, this one is acetic acid, this one is benzoic acid. And then it would also be HClO and HF. And also H3PO4. Remember, the definition of a weak acid is just an acid that does not dissociate 100%, meaning that of the acidic hydrogens, they do not all dissociate in solution. Your strong bases in this list is going to be NaOH. And that's going to be it. And then your weak bases is going to be your HCO3. That is baking soda. That's sodium. That is bicarbonate ion here. It's going to be NH3. In this sense, NH3, because we're talking about in water here, NH3 is a weak base. It is a Lewis base, as in it donates electrons. And that is it for the weak bases. And then there's one last species, which is going to be neither, and that is NaCl. Salt. Table salt is neither acidic or basic. All right, number 2 asks us to draw the Lewis structures of perchloric acid and phosphoric acid and to explain which one is stronger. So perchloric acid is going to have a chlorine atom at the center, surrounded by 4 oxygens, 3 of them double bonded, 1 of them single bonded. Phosphoric acid is going to be phosphorus centered with 4 oxygens around it, 1 of which is double bonded. The rest are single bonded with a hydrogen on that oxygen. Okay, so if we were to, let's talk about the phosphoric acid first. If we were to deprotonate this hydrogen, that would give us a minus charge here. If we look at resonance stabilization, there's only one other resonance form available here. We can kick in these electrons into here, which would then form a double bond, which would then kick this double bond out to here. And there would be 3 lone pairs around that oxygen. So there's one resonance form here if you lose one hydrogen. Perchloric acid, on the other hand, if we take away this hydrogen, these electrons can kick into here, and then you can have 3 more resonance form here. You could have this double bond kick out. You could have this double bond kick out. Or you could have these electrons and this double bond kick out. And what you're gonna have is this happen over it. The reality is these electrons are going to be delocalized around this entire molecule. So this whole area, the entire negative charge will be evenly dispersed around it. Whereas the phosphoric acid, the negative charge is going to be confined to a much smaller area. And remember what we learned during lecture is that if you can take a charge and spread over a larger area, you're going to have a more stable species. And that's what happens here, and that is why perchloric acid is strong and phosphoric is weak. Now, weak acid does not mean benign. Phosphoric acid is very corrosive. You would not want to get it on you. But it is weak in the sense that it only gives off, it does not give off the hydrogens very, very easily. Okay, number 3 asks us to find the pH of the following solutions. 0.25, molar HCl, 0.001 molar HCl. Then we got 0.25 molar NaOH and 0.001 molar NaOH. So to find the pH, we can use our equation that we learned. pH is equal to the opposite of log of the concentration of H+. So to find the pH of HCl, it's quite easy. All we do is take the opposite of log of both of these. And we end up with, this one is going to be 3. That one's easy enough to do in your head. And the top one is going to be 0.60. And that is your pH for those two. Now, NaOH. We're going to have to approach this one differently because the pH is defined as a concentration of H+. So we're going to have to keep in mind that the autoionization constant of water is going to be equal to the concentration of H+ times the concentration of OH-. So to solve these, the first thing we would have to do is find the concentration of H+ using this formula here. So if KW, so what we can do is we can rearrange this and divide KW by OH, and that would equal H+. We divide each side by OH, and we end up with that equaling H+. So it would be KW is 1 times 10 to the negative 14 over, now our concentration of OH is 0.25. So if we do 1 times 10 raised to the negative 14 divided by 0.25, what we're going to end up with is 4 times 10 to the negative 14th. Now this is equal to the concentration of H+. So to find the pH of this, now we just take the opposite of log of 4 times 10 to the negative 14. And that's going to be equal to 13.4. So your pH of a 0.25 molar solution of sodium hydroxide be 13.4. The next one's going to be the same way. It's going to 1.0 times 10 to the negative 14th divided by the concentration of OH, which, because NaOH is a strong base, can be 0.001. And 1 times 10 raised to the negative 14th divided by 0.001 is equal to 1 times 10 to the negative 11th. This is equal to the concentration of H plus again. So now to find the pH, all we do is take the opposite of log of this, which is opposite of log of 1 times 10 to the negative 11th. And the pH of this one is going to be equal to 11. So there are your pHs for all those solutions. And it's easy to find because it is they are strong acids and strong bases here. Okay, number 4, now we're going to get into weak acids. So we're going to have to find the pH. So we need to find the pH of a 0.25 molar acetic acid solution. And the pKa is equal to 4.75. That's given to us. So we're going to need to solve for equilibrium here. So remember that the Ka is going to be equal to the concentration of H plus times the concentration of the conjugate base over the concentration of HA. So what this looks like, if we simplify it, is Ka is equal to x squared, because H plus and A minus are going to be in equal quantities over HA. So first thing you do is need to solve for Ka. Well, pKa is simply the opposite of log of Ka, so which means we can take, to find Ka, we can take 10 to the opposite of the pKa, which is going to be 10 to the negative 4.75. 10 raised to the negative 4.75 is equal to 1.78 times 10 to the negative 5th, and there is Ka. So now we want to set up an expression. 1.78 times 10 to the negative 5th is equal to x squared over the concentration of HA, which is 0.25 minus x. Now, in this particular case, we can use the approximation method because Ka is less than 1 times 10 to the negative 4th. It's 1.78 times 10 to the negative 5th. So it's almost 10 times smaller. So we can ignore this minus x here, and what that does is that prevents us from having to solve the quadratic. So now the next step here is going to be just to multiply both sides by 0.25. And what that will give us is 4.45 times 10 to the negative 6 is equal to x squared. Now we can take the square root of both sides, and what that will leave us with is x is going to be equal to 0.002. Now this is our concentration of H plus. So if we want to find the pH now, all we do is take the opposite log of this number. So the pH is going to be equal to the opposite of log of 0.002 and we are going to get 2.68. So your pH in your answer for number 4 is 2.68. That would be the pH of a 0.25 molar acetic acid solution. Last problem, number 5. This one we are going to have to solve the quadratic for. We are asked to find the pH of a solution of dichloric acid, which you're not given a molarity here. That is my bad. So I'm going to show you how to work this problem with we'll do a 0.25 molar solution just like the other one. So we're going to have 0.25 molar of dichloroacetic acid, and what that looks like here is this versus normal acetic acid, which looks like this. Now, notice the difference in pKa. So the pKa for this one is 4.75 and this one is 1.26. That is this one is about 1,000 times more acidic than this one. The reason for that is the presence of these chlorines. These chlorines are electronegative and they pull these electrons away from the carbonyl here. And that makes the oxygen in turn pull the electrons away from the hydrogen more strongly, which then causes the hydrogen to be released easier, which is why dichloroacetic acid is so much stronger. So if you had only one chlorine here, the pKa would be higher. If you added one more chlorine, let's say this was a chlorine, the pKa would be even lower because it would be even more acidic. So we have a 0.25 molar of dichloroacetic acid, and the pKa for that is going to be 1.26. Okay, so like last time, we're going to set up an expression. So the pKa is just the opposite of log of the Ka. So to get the Ka, we just need to go 10 to the negative 1.26, which is equal to 0.055. And now we can set up our expression. So there's only one acidic hydrogen here. So we're going to have x squared, right, because H plus times A minus over the concentration, which would be 0.25 minus x. First step is going to be to multiply both sides by 0.25 minus x. And what that will do is get rid of the 0.25 from the bottom here. So what that gives us is let me write that in blue, 0.0137 minus 0.055x is equal to x squared. Now what we can do is subtract x squared from each side, and that will give us 0.0137 minus 0.055x minus x squared is equal to 0. Okay, now we can solve our quadratic equation here. So we have the opposite of b plus or minus the square root of b squared minus 4ac, and the whole thing is over 2a. So here we have a, b, c. And let's see, I'm going to type this in. I haven't figured it out beforehand, but if we have 0.055 squared minus 4 times -1 times 0.0137. Take the square root of that. So the inside of this right here is equal to 0.24. So now we can take the opposite of b, which is going to be positive 0.055. Minus 0.24, and that gives us a negative number, which is okay in this case because we're going to divide by a negative number here, because a is equal to -1. So we're going to divide by -2. So if we do 0.055 minus 0.24, that gives us negative 0.185 divided by a -2. And what we find out is our answer for x here is going to be 0.0925. All right, now that is going to be our concentration of H+. If you were to take the opposite of B, which would be plus 0.055, add 0.24 to it, and then divide by -2, you'd end up with a negative number, and that would not be the correct answer here, right? You can't have negative concentrations. So this is our concentration. So to find the pH, we just need to take the opposite of log of this. So the opposite of log of 0.0925 is equal to 1.03. So your pH here for a 0.25 molar solution of dichloroacetic acid would be 1.2H. All right, so that is all the homework problems for this chapter. If you have any questions, you can email me. I hope that you're all doing well and you understand this material okay. Next lesson is going to be on buffers, and that will lead us into biochemistry.